This problem looks like a simple greedy merge. But the catch is brutal. You don't choose which pair to merge. The minimum adjacent sum is always forced. To solve this efficiently, we need priority queue, a linked list simulation, and a smart way to track when the array becomes sorted. This is classic hard-level greedy simulation. We are given an array nums. Operation forced. Find the adjacent pair with the minimum sum. If multiple, pick the leftmost. Replace them with their sum. Goal is return the minimum number of operations to make the array non-decreasing. Constraints are n is less than or equal to 100,000. Values up to 10 to the power of 9. We must avoid big O of n squared. Simulation. Let walk through an example nums is equal to a list containing 5, 2, 3, and 1. Violations. 5 is greater than 2. 3 is greater than 1. The minimum adjacent sum is the pair 3, 1, which equals 4, so a merge is forced. The array becomes 5, 2, 4. There is still a violation. 5 is greater than 2. The next forced merge is the pair 2, 4, which equals 6. The array becomes 5, 6. The array is now sorted. Total operations is 2. Why brute force fails? After each merge, adjacency changes. Recomputing minimum sum every time is too slow. Rebuilding arrays is expensive. Two things matter. 1. Which adjacent pair is the smallest min heap? 2. Is the array sorted yet? Count violations. Instead of checking the whole array every time, we track how many decreasing pairs still exist. When violations reach 0, we stop. We simulate the process efficiently using data structures used. Min heap. Used to always select the adjacent pair with the minimum sum. Array-based linked list. Enables fast removals and merges without costly shifting. Violation counter. Tracks the number of out-of-order adjacent pairs, disorder, in the array. Let walk through the code. Early exit. If all adjacent elements are in non-decreasing order, return 0. If the array is already sorted, no operations are needed. Linked list simulation. Initialize 3 arrays. RMV. A Boolean array of size n initialized to false, used to mark removed elements. PRV. Where PRV I stores the index of the previous element, I-1. NXT. Where NXT I stores the index of the next element, I+1. Or -1 if there is no next element. We avoid deleting elements. Instead, we skip removed indices using pointers. Min-heap initialization for each index I from 0 to n-2. Store the pair, nums, I plus nums, I+1, I. Use a min-heap so that the smallest adjacent sum can be accessed efficiently. Heap stores, sum, left_index, for each adjacent pair. This guarantees we always process the forced merge. Violation counter. Count the number of adjacent pairs where the left element is greater than the right. Store this count in bad. This tracks how far we are from sorted. Main loop. Repeat the following steps while there are still violations, i.e., while bad is greater than 0. Stop as soon as the array becomes non-decreasing. Lazy heap validation. If the current element I has already been removed, or if it has no next element, skip this iteration. Heap entries may be outdated. We skip invalid merges safely. Before performing a merge, remove any violations involving the current element and its neighbors. The pair, previous, I. The pair, I-J. The pair, J, next. This ensures that the bad counter stays accurate. Merge step. Set nums, I to the merged sum. Mark J as removed. RMV, J equals true. Update the next pointer of I to skip over J. NXTI equals New Jersey. This is a classic linked list removal, where the element J is deleted and I now points to the next valid element. Adding new violations. After merge, new neighbors might violate order. We update bad accordingly. Heap updates. After a merge, only the adjacent pairs near the merged element are affected. Therefore, we push the following new pairs into the heap. Previous, merged. The pair consisting of the previous element and the newly merged element. Merged next. The pair consisting of the newly merged element and the next element. This keeps the heap up to date without rebuilding it entirely. Given an array nums, we want to sort it by repeatedly merging adjacent elements, replacing them with their sum, while counting the minimum number of operations needed. Step 1. Handle already sorted array. If all nums I 0, sum I equals heap.heappop, heap. Repeat while there are still violations, bad 0. Pop the adjacent pair with the minimum sum from the heap. If RMV I or NXT I equals -1, continue. J equals NXT I. If RMV J or nums I plus nums J equals sum, continue. Skip elements that have been removed or are invalid. Ensure the sum in the heap is still valid. It may be outdated. Step 4. Remove old violations. Pi equals PRVI. New Jersey equals NXT J. If pi equals -1 and not RMV pi, and nums pi and nums I, bad dash equals 1. If nums I and nums J, bad dash equals 1. If New Jersey equals -1 and not RMV New Jersey and nums J and nums New Jersey, bad dash equals 1. Before merging, subtract violations involving previous J next. This ensures bad remains accurate. Step 5. Merge the pair. Nums I equals sum. RMV J equals true. NXTI equals New Jersey. If New Jersey equals -1, PRV New Jersey equals I. Merge the pair IJ into a single element sum at index I. Mark J as removed. Update the linked list pointers, NXT and PRV, to skip J. Step 6. Add new violations. If pi equals -1 and not RMV pi, and nums pi and nums I, bad plus equals 1. If New Jersey equals -1 and not RMV New Jersey, and nums I a nums New Jersey, bad plus equals 1. After merging, check new violations created with the neighbors. Update bad accordingly. Step 7. Update heap. If pi equals -1 and not RMV pi, heap.heappush, heap, nums pi plus nums I pi. If New Jersey equals -1, heap.heappush, heap, nums I plus nums New Jersey I. Only the local adjacent pairs near the merged element are affected. Push the new sums into the heap. Previous, merged, merged next. Step 8. Count operation. A plus equals 1. Increment the operation counter each time a merge is performed. Step 9. Return result. Return op. Once all violations are gone, bad equals 0, return the minimum number of merge operations. This problem is about forced greedy simulation. Key interview takeaways. You don't control merges, the heap does. Track violations, not full sorted checks. Use linked list arrays to avoid costly deletions. Validate heap entries lazily. If you understand why bad works, you truly understand this problem. Time complexity. Each merge operation requires updating the heap, which takes O log n. There are at most n-1 merges, since each merge reduces the array size by 1. Overall time complexity, O, n log n. Space complexity. We use a heap and several arrays, RMV, PRV, NXT, each of size n. Overall space complexity, O, n. Conclusion. This solution handles arrays of size up to 10 comfortably.